Take a quick look at the homework that we had last night on page 553, questions number 1 to 9. I know that we had a couple issues with this. Any specific requests here to go over questions here, Max? 5? Okay, Patrick? 259, 8B. 259, 8B, going once, going twice. Okay. Number 2, why was it necessary to introduce a field theory? Well, let me kind of point you in the right direction on this and then see if somebody can give you the right answer for this, okay? We talked about the difference between a field and a force, right? Okay. What's the difference between a field and a force? Yep. Right. A field is always there. A force is only there if there's something to experience it. So, with that kind of seed in your mind now, can anybody tell me why it was necessary to introduce a field theory? Not a force. Let's not say force. There's not still a push or a pull, even if the object isn't there. But there's still something there, right? There's still the thing that causes it. And there may not be an effect on anything else if there's nothing else there to experience it. But whatever was caused is still there, right? So we have to introduce, or we had to introduce the idea of field theory to help us to understand, to help us to explain that there's something still there, even if there is no longer a force. As long as you have the thing that produced it, the force has disappeared if the experiencer is gone, but something, whatever it was caused by the producer, is still there, okay? Number 5, if vector arrows can represent an electric field at a point surrounding a charge, identify 2 ways that the vector arrows shown below represent differences in the electric fields around the 2 source charges. Okay, so we've got a source charge right here that's negative, a source charge right here that's positive. At a point P, we have 2 different fields there. Field that points this way, a field that points this way. What are 2 differences between the electric fields surrounding those 2 charges? One of them is really, really obvious. Okay, so there's a direction difference, right? Okay, this one is toward the producer, and this one is away from the producer. That's probably the most obvious one there. Okay, the direction. And electric field is a vector field, so certainly direction is important. Okay, it's different here because we have a different kind of producer. What's the other difference? This one's a little bit more subtle, but still kind of staring us in the face. Although sometimes that's a problem when it's staring us in the face because we overlook the things that are staring us in the face. Yep, Max? Yep. Yes, yeah. When we represent a vector, we try to represent the vector by an arrow that is proportional to the length of the arrow, proportional to the strength of the vector, right? Since this one is longer than this one, then the strength of this field is stronger than the strength of this field. Okay, does that make sense? What does that tell you about the strength of the charge, this negative charge, as opposed to that positive charge? What's the value of this charge? We don't know its exact value, right? But we know that it is what in comparison to this one? We know it's higher, right? Because that distance, point P, looks to be the same distance away from the charge. If the field strength caused by the negative is the same distance away as the field strength caused by the positive is stronger, then the producer must be a bigger charge as well. All right, next question, number 9. Sorry, number 8B, I should say. Small test sphere with a negative charge of 2.5 microcoulombs experiences an electrostatic attractive force. I'm going to circle attractive force too. Okay, I have this feeling that might end up being important later on. This value, when it's placed at a distance 0.0400 meters from another larger charged sphere. Calculate the magnitude and direction of the electric field at this point. The magnitude and the sign of the charge on the larger charged sphere. So nobody asked me for 8A. What was the answer to 8A, if you guys are okay with that one? What's the magnitude and the direction of the electric field at that point? Okay, 2.04 times 10 to the 4 newtons per coulomb. That's the field that's produced by, let's see here. Oh, sorry, that's the electric field that's experienced by this charge right here, by this negative charge, right? That's how you did it, right? Is the electric field experiencer equation, E is equal to F over Q. You've got F, you've got Q. We solve for the electric field strength experienced by that. Now, we know that the electric field experienced by that charge is also the same as the electric field that's produced by whatever the producer is, right? Now, what are we trying to find in B? The magnitude and the sign of the charge of the larger charged sphere. This is the one that's causing it, right? Well, we're probably going to use the equation E is equal to KQ over R squared for that. We have R. R is 0.040 meters. We have K. We want to find Q. Okay, we want to find Q. What's the value of E? What's the value of the field caused by this producer? Do we know? We just said it, right? What is it? Right, we just said that the field that's experienced by this guy out here at this point is the same as the field that was produced by the larger charged sphere, right? So we know this value as well. It's 2.04. All we have to do is solve for Q now. Rearrange that equation. It becomes E times R squared over K equals Q. Now, I'm not sure what the value of that is, okay, but we can probably plug numbers in there and solve for that. What about the sign of it? What about the sign of it? Things like this get a little bit tricky. To me, it's helpful to draw a little diagram in a situation like this. Okay, we have a test sphere that's negative. Okay, here's my producer. We don't know what it is, positive or negative. Okay, we have a test sphere that's negative. We know that it's an attractive force. Right? It tells me it's an attractive force. So that little bit that I underlined right there did become relevant. It's an attractive force. If the force on this negative charge is toward this bigger charge, then what do we know about that bigger charge? It's got to be positive, right? Because a negative is not going to be attracted to a negative. So it's got to be positive. If the force is towards the positive, then which way would the field be? This isn't really asking the question, right? But which way would the field be pointing? Away from it. Hey, does that all make sense? The field points away from the positive producer. Which way does the negative go? Opposite to the direction of the field, which we talked about the first day we introduced fields, right, Travis? All right, finally, number 9. The negative charge on a negative charge, of 3 millicoulombs is 1.2 meters to the right of another charge that's 2 millicoulombs. Negative charge, 2 millicoulombs. Oh, this one's negative as well. They're both negative. What's the net electric field midway between? Oh, B is the one you had trouble with, I bet, right? Yeah, we did a question like that with forces. Remember that? Remember that one? Let's copy this one over and get a little bit more space to work here, okay? So let's draw this out here. We've got charge 2, we'll call it, negative 3.0 times 10 to the minus 3 coulombs, 3 millicoulombs. There's another one that's, we'll call it charge 1. It's negative 2 times 10 to the minus 3 coulombs. And they're 1.20 meters apart. In question A, we want to find the field strength there. Was it question A and B that somebody asked for, or just question B? Both of them? Okay. So we want to find the field strength right there at point X. Okay. The field caused by number 1 is going to be to the left because it's toward a negative producer. The field caused by number 2 will be to the right because it's toward a negative producer. Let's get the value of both of those fields. Okay, and that part of it's relatively straightforward. E1 is KQ over R squared. We're dropping the sign of the charge as we always do in an equation. The distance here is going to be 0.60 meters, and we got to square that. Who has a value for E1 there? What is it? 4.99 times 10 to the 7 newtons per coulomb. Let's find the value of E2. I'm going to use the same method there, right? KQ over R squared. This time Q will be 3. So it's That's going to give me somewhere around 7.49 times 10 to the 7. Is that right? Right? Which all I did there was multiplied it by 1.5, right? Because this charge is 1.5, what the other one is. Sometimes you spot a little shortcut cut like that and saves you a little bit of time. Okay? But if you don't, then don't worry about it. It just takes you 20 extra seconds to punch it into your calculator. Let's add these up now. The net field is equal to E1 plus E2. E1 is negative 4.99 times 10 to the 7, and E2 is positive 7.49. And that's going to give me 2.5 times 10 to the 7 newtons per coulomb. About. Good? Is that okay? Yeah, that's not, I was going to say that's the easy one. It's not the easy one. That question's not an easy question, but that's the more straightforward one. Question B is the real challenge one here. Okay, the real tough one. B asks us for the point along the same line between the two charges where the net field will be 0. So let's draw that again. Okay, this was number 1, this was number 2. This was negative 2 times 10 to the minus 3 coulombs. This was negative 3 times 10 to the minus 3 coulombs. Okay, we want to find a point in here somewhere, not midway between. We want to find a point in there somewhere that's not midway between where the field strength is 0. Well, we know once again that the field caused by number 1 is to the left. The field caused by number 2 is to the right. Okay, we essentially want field number 1 to be equal to field number 2, or at least the magnitudes of them. Okay, if we want the field strength to be 0, then they have to balance each other. They have to cancel each other out. Let's make this distance right here r. Okay, if we do that, then E1 will be KQ over KQ1 over r squared. E2 will be KQ2 over, not r squared, what's it going to be? 1.2 minus r squared. Good. 1.2 minus r. Now let's square that whole thing, right? 1.2 minus r in brackets squared. The k's cancel here. Q2, okay, I don't know if any of you guys spotted this, but Q2 is the same as 1.5 of Q1, which allows us to cancel Q1. Anybody catch that? If you didn't, it's okay. Plug in the value of Q1 and plug in the value of Q2. Okay? Just is a little bit uglier calculator-wise, but it ends up being the same thing. Absolutely. Absolutely. Can you cancel it to 10 to the minus 3 if you plug in the values? I think we did that on that force problem that we had a week or so ago. You can, anything that appears in both in every term on both sides, you can cancel it, including exponents. Okay, so that makes it, not a lot more work than what I just did, right? If you cancel out the exponents. So this becomes 1 over r squared is equal to 1.5 over 1.2 minus r squared. Let's cross multiply here. We end up getting 1.2 minus r squared equals 1.5 times r squared. Right? We took this up by multiplying. What's the easiest way to deal with this now? Square root it, right? So we get 1.2 minus r equals whatever the square root of 1.5 is. I'm not sure what that is. What's it going to be? 1.2247. Okay. Times r. Let's take this over by adding because it's subtracted from the left side. So that gives me 2.2247 r. And we solve for r, it's 1.2 over 2.2247. So somewhere around 0.4-ish. Is that right? What do you get for that? 1.2 divided by 2.2247. 0.539 meters. So where is that point? 0.539 meters to the right of the first charge. So the other distance is going to be what? 0.661. Okay. Okay. So if you had to solve for, if you had to call this R, right, instead of this, and you could have done that, then you would have solved for a value of R that was 0.66 instead of 0.53, 0.539. Good. Tough question, right? Tough question. As I told you with that force question that we saw a while ago, I don't think you'll get one like that on an exam because I think it's mathematically too tricky. Okay, conceptually, it's absolutely fair game. Recognizing that those two fields have to be equal and so on, balanced, so on. Mathematically, I don't think you'll see that. We're going to go just a little bit further with the electric fields here now and introduce one more equation. But first, I want to review quickly the equations that we've seen so far. The electric field that is experienced by a charge is going to be F over Q. Now, if we have two parallel plates, we have a uniform electric field. That's unlike any electric field that we've dealt with so far. It's a uniform electric field. The field, by the way, between the two parallel plates would look like this. We know it's uniform because the field lines are parallel. Does the same equation apply to a charge experiencing an electric field in between these parallel plates as, say, a negative charge experiencing a field out here somewhere in this non-uniform field? Well, the simple answer is yes. The electric field experiencer equation is always valid, whether you have a non-uniform field, which is the kind of field that we've seen up until this point, or a uniform field, which is the new kind of field that we're seeing, the field that acts between two charged metal plates. E is equal to F over Q still applies. Now the producer equation, E is equal to KQ over R squared, I've capitalized all this stuff, right, because it's really important. You cannot use that in this context. You cannot use that with parallel plates. The reason is because E changes with R. E changes with the distance from the producer. E is not a uniform field. It's not a constant field if it changes. Okay, here in these parallel plates, it doesn't matter where the charge is. The field lines are parallel, and the field is going to be the same no matter what. If the field is the same no matter what, then this equation that says the field changes depending upon where the charge is can't be valid. So we've got an experiencer equation that's valid here and here. We've got a producer equation that's valid only here when we have a non-uniform field. Well, then we need another equation that's valid for a uniform field. By symmetry, right? If we have two equations that are valid for a non-uniform field, okay, the field that we've been dealing with up until this point, then we need two equations that are valid for a uniform field. The equation that you see on the bottom is the one that's valid for parallel plates or things that approximate parallel plates, anytime you have a uniform field. Now, there's a couple variables in there that might seem a little bit foreign to you right now. Delta V. Delta V stands for what we call the potential difference between the plates. The units for that are going to be volts, capital V. Now, you don't know what that means right now. I'm going to tell you kind of what it means, and then in a couple of days, we're going to describe that in more detail. Okay? For now, just trust me that it relates to the energy of the charges, the difference in energy of the charges. So it's not energy, but it's related to the energy. Okay, and that's good enough for now. Again, in a couple of days, we'll be a little bit more specific on that. Delta D, that's not the distance from one of the plates. Okay, if we're going to use the distance from one of the plates, then we might as well use this equation. Right? If the distance from one of the plates changed the value of the electric field strength, then it wouldn't be a uniform field. It would be a non-uniform field. So the distance between the plates is what we're going to call delta D. And that's going to be measured in meters. So this distance right here, basically. Again, it doesn't matter where the charge is, if there even is a charge in between those plates. It doesn't matter where it is, because the field strength is simply dependent upon the potential difference between the plates, the difference in energy of the plates, basically, divided by the distance between the plates. And as long as that's not changing, then the field strength anywhere in there is not going to change either. So what I like to do at this point is, we got 3 equations now for electric fields. For the math people in here, I like to draw a little Venn diagram. Here we got our first equation. This is our producer equation, right? KQ over R squared. Here we have our experiencer equation. E is equal to F over Q. And here we have our new equation. E is equal to delta V over delta D. The first 2 equations are valid for a non-uniform field. In other words, in all the questions that we've dealt with so far. The last 2 equations are valid for a uniform field. And the new questions that we're going to see involving parallel plates or uniform fields, things that approximate parallel plates. That middle equation, E is equal to F over Q, the experiencer equation, it's valid whenever, all the time. Okay, whether it's a uniform field or a non-uniform field, whether you know what kind of field it is or not, it doesn't matter. If you have a field and an experiencer, then you're going to use that second equation, or at least you're allowed to use that middle equation. This is just a little summary of it, guys. Use your judgment on whether you need to copy this down or not. In essence, it's all a repeat of what we've said already. 3 equations, right? Okay, here's my Venn diagram again. Okay, non-uniform field. And on the bottom one, the bottom 2 are valid whenever we have a uniform field. We can use the first one around a producer. The second one we can use in the context of one of those producers, except we have to have information about the experiencer. So not when we have data about the producer. Can't use this one around a producer for sure. This is the experiencer equation, right? Well, we can use this one in conjunction with the experiencer equation, certainly, if we have an experiencer. Parallel plates? No. Yes. And of course, we can use this one for parallel plates as long as we have something experiencing those parallel plates. So again, don't feel like you need to copy this down, okay? If you've got everything and it's all good for you right now, then this is just a summary again of what we've already said and what we've already written down, but whatever you need to do. Okay, let's take a look at one example, and that's where we'll wrap it up for the day here, okay? 11.9 on page 516, it says a cathode ray tube computer monitor accelerates electrons between charged parallel plates. I think we talked about this briefly one day, didn't we? The computer monitor, maybe it was with the other class. Did we? Yeah. Yeah, it was the idea of the negatively charged air pollutants being repelled by the screen, right? Which gets blown into your face, okay? The old style computer monitors and the TVs, the one that you see up in the corner there, okay, the electrons go from the negative plate towards the positive plate, then they go through a little hole, they hit this screen. Okay, that's what causes the screen to glow, is these electrons hitting this phosphorescent paint. That's what causes the picture that we see. But it also leaves a whole bunch of electrons on that screen sometimes, leaves it negatively charged. Okay. If you have one of those old TVs in your basement or your bonus room or whatever, sometimes after you've had it on for a while, and you take your finger, okay, you hear it discharging. You hear those electrons discharging into your finger. Okay, so that's how the cathode ray tube works. Now, this question is simply telling me that the plates way over here that accelerate the electrons, that get the electrons moving to the speed that they need to get to, are 1.2 times 10 to the negative 2 meters apart. They're also telling me the potential difference is 2.5 times 10 to the 4 volts. That's going to be delta V. They're calling it V right there. We should call it delta V. Right now, you're not going to really see what the difference is between V and delta V, but you will. Okay, so it's not really V, it's delta V. We want to find the electric field there. The electric field. Well, we have a uniform electric field here, and you can see that by the diagram. Even if they didn't label or draw the electric field, we know that it was a uniform field because it's parallel plates. That means the first equation that we learned, the producer equation, we're not allowed to use here. But we are allowed to use E is equal to F over Q, and we're allowed to use E is equal to delta V over delta D. Those bottom two equations are perfectly valid. Now, we're not necessarily going to use both of them. Depends upon what we have given to us. But they're both valid. We don't know anything about the experiencer here. So that middle equation that is valid, we're probably not going to use here because we don't know anything about that experiencer. We do know something about the plates themselves. E is equal to delta V over delta D. The potential difference between the plates is 2.5 times 10 to the 4 volts. And the distance between the plates is 1.2 times 10 to the negative 2 meters. Do the math on that one, and we're going to get 2.5 divided by 1.2 is 2 and 1/12, 2.08. Is that right? 2.08, 2.1, I guess it would be, right? 2.1 times 10 to the 6. Oh, look at the units here, though. What should the units be for this one? Why can't we use newtons per coulomb? Hey, that's the units for electric field, right? But there's now another set of units that I could also use that mean exactly the same thing. What are they, Dallin? Right. So 2.1 times 10 to the 6 newtons per coulomb. Keep using that if you want. Okay, that's the units we've been using. Those are the standard units. We're allowed to keep doing that, but we can also call it a volt per meter. There's no conversion to do there because 1 newton per coulomb is the same thing as a volt per meter. So whatever you want to call it is fine. Don't worry about converting anything. Just call it whatever units you're most comfortable with. But listen, if you're going to continue using newtons per coulomb, that's fine. But make sure that you recognize volts per meter is a unit for electric field, because you might see that given to you sometime, and you might have to recognize that that's electric field. Okay? All right, your homework for tomorrow. Nice, easy set of homework tonight. Just page 568. And I think both pretty straightforward questions. Okay. I'm going to assign a little bit of homework for Monday, though. I don't want to assign this for tomorrow. Let's go worksheet number 8 for Monday. So you got a few extra days to do worksheet number 8. All right, that's it for today.